Alright, so in this video we're going to be talking about properties of the definite integral. And so I've written up here the first property, or part of the first property. We want to compare what happens if I take the integral of a to b, f of x dx, and compare that to the integral from b to a, f of x dx. Now, here's a hint on the first one, right? We're going to be taking the limit as n goes to infinity of the sum I equals 1 to n of f of xi star, and then the next one is going to be delta x. Now if we take equally spaced intervals, that'll be b minus a over n, right? On this side, let's see what that sum looks like. In this side we're going to have a minus b over n. So what's the difference between these? Well, this value is just the negative of this value, right? And so our first property then is that if you reverse the bounds, on the definite integral, put a minus sign in front. Good. And so another way to think about it, right, is that if this is your function, right, from a to b. Then to find the area, right, if you go from b to a, you're going in the reverse direction, right, instead of from a to b. And so that's why the negative sign's there. Okay, next property is that the integral from a to a, f of x dx, is equal to, can you guess? Because I have f of xi star, I got my sum, and now my delta x is going to be a minus a over n, which is equal to 0. That's right. So the integral from a to a, and of course geometrically, right, what are we doing in that case? You're finding the area under a point. The area under a point would have your rectangle would have 0 width, for example, and so then the area would be 0. Good. The next one, a to b c dx, we've already talked about. Just as a reminder, do you remember what it was? If you have a function c from a to b, it's just the area of that rectangle, and so that's going to be c times b minus a. Very good. 4. What happens when I integrate f of x plus or minus g of x dx? Well, the integral really is a sum, right? And so when you take the sum of a sum, you can rearrange the sum pretty much, generally speaking, any way you want. We have to be a little bit careful about that, but we'll just assume that is true. And so if you can rearrange your sum, then you can distribute the integral through just like we distributed the sum through. And so this is going to be the integral then from a to b. Oops, my thing is moving here. F of x dx plus or minus the integral from a to b, g of x dx. Good. All right, I'm going to pause for a sec. Okay, the next one is very similar. If you're integrating c times f of x, then you can factor the constant out, just like we did in the sum. So we can factor the c out of the sum, take that f of x dx. Caution, while we're here, how about, can you do this? Is this a valid thing to do? Oop. Is this the same thing as x times the integral from a to b f of x dx? Are these two things the same? They are not, right? Because x is not a constant. Okay, so this property is only true for constants. Good. Okay, now if I integrate from a to b f of x dx, and c is any other point, then I can rearrange, or I can rewrite the sum as the integral. I can break apart the integral and take the integral from a to c, f of x dx, plus the integral from c to b, f of x dx. And so geometrically what that's saying, right, if you're, I'm assuming by the way that c is in between here. So the area from A to C, you can write the area from A to B as the area from A to C plus the area from C to B. Good, so you can break apart your area into pieces if you want, and just find the integral of each piece separately. Good. 7. Suppose that f of x is greater than or equal to g of x for all x. For all x in AB. Then what do you think we can say about the integral from a to b f of x dx versus the integral from a to b of g of x dx? Well, the areas are going to match. This is called the comparison property. Okay, so if one function is bigger than the other, then the integrals are also going to be bigger than the other. Okay. So similarly, if you can take a small number m and bound f of x between a small number m, so this is like the minimum, and capital M would be like the maximum, and then integrate all three of these expressions, what do you find? Well, the integral of the left-hand side, remember by a previous property, would just be the area of this rectangle. And same thing for the upper side, right? And so then you would have the integral in between. Good. And so geometrically, you can kind of think of it in this way too. If this is your function, if this is the, so this is our graph from A to B, right? This is our max, so this would be like your capital M, and this is like your little m. And so you can see that the area under the curve is going to be, let me draw these in different colors maybe. The small rectangle will be this rectangle. This is little m, right, times b minus a. And then the big rectangle, maybe we'll do in green. This will be your big rectangle. And so this is this side. And so the integral in between, we could say is red. And so that's this area, right? Okay. Hopefully that's not too much. You can kind of see the difference there. All right, so now we want to use these properties and try out a few examples and exercises. 1 second, I'll pause and I'll write up the first problem. Okay, so in this first problem, we're told that the integral from 1 to 5 of f of x dx is equal to 12, and the integral from 4 to 5 of f of x dx is equal to 3. And we want to find the integral from 1 to 4 of f of x dx. Well, if you're not sure about this, let's just draw a quick picture and just draw some arbitrary function. We're going from 1 to 5. And so this first one is saying that this full interval, or full area from 1 to 5 is equal to 12, right? And so that's this one. So this full area is 12. And now this integral just represents the area from 4 to 5, right? And so this area is 3. And so what does this area represent? Well, this is this area, right? So from our properties, then we know that the integral from 1 to 4 of f of x dx plus the integral from 4 to 5 f of x dx is equal to the integral from 1 to 5 f of x dx. And if we just go ahead and plug in our numbers then, this is equal to 12, this is equal to 3, and then let's just bring the integral down so that the integral from 1 to 4 f of x dx is equal to 12 minus 3, which is 9. Good. All right. Okay, so I've defined my function f of x here to be the integral from 1 to x f of t dt, where this picture is giving you the graph of f of t. Good. So what does this represent here? So for example, if x is equal to 2, what is f of 2? F of 2 would be the integral from 1 to 2, f of t dt. Now, is that going to be a positive or negative number in this graph? I think you'll see, right, that that's going to be a negative number. What is f of 1 in this graph? Well, using our definition, right, that's the integral from 1 to 1 of f of t dt. And how big is that? Did you say 0? Yeah, because the integral from 1 to 1 is going to be 0. And so what is f of 0 going to be? That's the integral from 1 to 0 f of t dt. And from this graph, you can see that the area from 0 to 1 is positive, but then what happens when you reverse your bounds? Yeah, this actually becomes negative. Right, this was negative up here too. Good. So that's going to be this quantity in a negative sense, right? And then we're going to go up to 0, and then we're going to get negative again. And so what would the function look like then generally? Oh, by the way, which is largest of these? And what happens when you go to f of 3? F of 3 is going to be even more negative, right? So it looks like f of 1 is going to be the max. And so 0 is actually going to be the max. And so if we take 0, 1, 2, 3, it looks like the function is going to do something like this, right? It's going to go up to 0, but then it's going to go down, whoops, it's going to go down to the same negative number, right, than before, but then it's going to keep going down. It's not going to level off like that. It's just going to keep going down until it gets to a kind of a maximum negative number. Good, because then if you were to keep the pattern going, right, you would end up gaining some positive area after that, so then this curve would just start going up again. Good, but up till this point, it looks like this is going to be the graph of capital F of x. Good, so this function f of x right here is going to play a special role in our next section. This is going to be called the area function, and so we're going to take a look at that more closely next time. I think we'll stop there. Yeah, I think we'll stop there. Try out the exercises in this section, and I'll see you later.